Right, now let's look at the ways we can use pointers and functions. Right? They're going to give us the ability to pass a memory address to another function. But we'll be using pointers in our parameter list. We'll also use pointers as return types. Right, but when we use pointers in our parameter list, we're going to be able to pass a memory address from one function to another. That will give then the function access to memory outside its scope by passing that pointer. Right? And then giving it access to that memory gives you the ability to read or to change the data content. So it all depends on whether you make the pointer read only or if you allow it to write as well. And then using pointers as function parameters will allow us to return more than one value from a function. Right. So let's go back and take a look at our swap function. Back when we first learned functions, we wrote a function called swap that had two parameters, A and B. And A and B were not pointers, they simply got a copy of the memory that was passed to them. And so we'll see then that we'll use a pointer to give a reference to memory area later and actually be able to affect the values of A and B outside here. So let me just bring up code blocks here. Right. So let's write that swap function. All right, so here in main, right, we have two variables. A, I'm going to set equal to some number. B is going to be equal to another number. All right, and we're going to call this swap function, and we're going to pass it the memory contents of A and B. And so then this function doesn't return anything. It's void called swap, right, int A, int B. And then we have this temporary variable in here, which is an int temp. We'll store A inside temp. And then we'll go ahead and set A equal to B. And then we'll set B equal to temp, right? And then we will just return back from this function. And what we're going to see is when we run this, that A and B are local to this function. Any changes we make to them in here don't affect the A and B down here in main. All right, so let's step through this now with a debugger. All right, so here we are in main. A and B have not been initialized yet, so if I just hit, we just go to the next line. All right, A now has 5, B has 7. All right, now we're going to step into the swap function. So we step into, all right, now that we're up in swap, notice swap has two function parameters, A and B, right? This A simply got passed the value of 5 because here in main, it read the 5 that's stored in A's memory and basically filled this in with this expression A became 5, this expression B became 7. And so this A was assigned this argument here, this B was assigned this argument here. Right, so now A and B are local to swap, right? They come into existence when we come into the function. Now we're going to declare temp, right? Temp is going to get the value of 5 stored in it. Now we're going to store 7 in A, and we'll put the 5 back in B. So up here in swaps variables, you can see that we switch the order, we swap them out. But now when we return back, so next line, when we go back to main, notice, right, A and B in main were not changed. Swap simply got a copy of the values that were stored in these variables. Right, they each have their own memory space on the stack, right? They each have their own scope. These came into existence here in swap. When we entered this function, they went out of existence when we left the function. Right. So we didn't actually change anything back in main's memory. Right. Now, let's see what happens if we make A a pointer to an int and B a pointer to an int. That means here in main, when I call this function, because this function expects a pointer, and here A is not a pointer, I can simply give it A's address, and I can give this B's address, because the address of A, right, is a pointer to A's memory. The address of B is a pointer to B's memory. So when we step into this function now, A will point back to main's A. This pointer B will point back to main's B. Right. And here now, if I want to access A, I have to use that indirection operator. And if I want to access B as well, we use the indirection operator. And here we use the indirection operator. All right, I don't have to with temp because temp is just an integer. And this says, this indirection operator says, go to where A points. So the star A says, go to where A points and return the value stored in that memory, right? Which this will be pointing back to the address of A here. All right, so let's try to run the cursor. All right, so here in main, actually, let's see if the debugger will actually let me. All right, so there's A's address, there's B's address, right here in main. All right, we're going to now step into this function. We can see this A and B, right, has a 5 and a 7 back in main. Next line. Oh, I hit next line and I wanted to step into. Let me start again. All right, let's step into this function now. All right, so now we step in here. So notice now, A in this function is a pointer, right? It's a pointer simply because we declared it with the star, and B is a pointer when we declared it with the star as well. So we said B is a pointer to an integer data type, A is a pointer to an integer data type. Right now, this says go to where A points, right? The indirection operator used here with A said go to where A points, which is back in mains A, right? And store that in temp. So now temp gets the value 5, right here. Now we're going to go to where B points here, right? This expression is evaluated. B points back to the address of B here. So dereferencing B is going to return a 7 here, right? So now what we did was we affected, right, where A is pointing. Now let's see if it likes, actually meant to do that in the launch window. So let me see if it'll type dereference A here and indirection B. All right, right now then they both have the same thing. Now we're going to overwrite the memory where B points. Right, we're going to store what's in temp there. And now we'll return back. Now that we're back in main, notice back here in main, A now has the value of 7, B has the value of 5. Their values did get swapped out simply because this pointed back to the memory in here, right? Here we gave this pointer the address of this A, we gave the other pointer the address of this B, and it swapped places in memory. All right, so that's the difference between pass by value. We call this pass by reference, right? We reference an address. Right, so when these are pointers and we pass an address, we call it pass by reference. That means that these pointers have the capability to refer to another area of memory, particularly since main called this function, it refers to this A and B here in main. Oh. All right, so that's one way then to use pointers as function parameters. Right. All right. Now let's see how we work with arrays as function parameters. So we're going to start out by writing a function that actually, well, let's write a function first that calculates the sum, and then we'll work with array as function parameters. So let's write another function here that's not in the notes. Okay. Let's write a function that receives 2 float values as parameters, as arguments, and returns the sum of those 2 values, right? All right, so I'm going to call this calcsum, and then it receives 2 float values as arguments. That means I have 2 things in my parameter list. They're both of type float. I'll call that A, and I'll call this B here. All right, and we said then this function should calculate and return the sum. Well, we could do that as simply as return A plus B. It's a very trivial function. And that will be returning something of type float, because when we add two floats together, right, that returns an A and a B. If we don't want to write it that trivially, if this is easier for you to see, we could say, go ahead and create sum, right, as a floating point variable. We could say sum is equal to sum is equal to A plus B. And then here we could say return sum. And because sum is a floating point type, right, we're going to return that. So that's one way we could write that. Let's just go ahead and write it the longer way like this. I'm going to get rid of the swap function, right? And now here, right, in main, we'll have float f1 equals 1.01 and float f2 equals 2.02. And we're going to just then make another variable. I could call it sum, I'll call it total, just give it a different name. And we want to assign to total what the function calc sum. So we call the function calc sum, and we're going to pass it f1, f2, right? And we'll see now that this will return the sum of these two numbers. Let's run the cursor here. All right, and next, no. I hit next line when I want to do step into. All right, let's step into for main. All right, so notice here in main, and actually let me delete these things that don't relate to this problem. All right, here's our values for F1 and F2. Right, step into, well, we come into this function now. So up here, right, we passed a copy of what was in F1. That's the first argument in the list, to A. So we can see A got the value 1.01. We passed a copy of the value stored in F2 to B. B has a value of 2.02. You can see a little rounding, or a little error here with the floats. We're going to add A and B together and store that in sum. Right? And now we're going to return the value from sum back here. Right, so this expression then results in that sum value, assigns it to total. So back here in main, now we have that total. All right, so that's how we'd write a function that has two parameters, right? It receives these two pieces of information, these two floats, right? It calculates their sum and then returns their sum. Right, now I'm going to stop this and let's do the same thing with pointers. We're actually going to make A a pointer to a float and B is going to be a pointer to a float. Because we make these pointers here, that means back here, you need to go ahead and say, all right, address of F1 and address of F2. We pass the address because a pointer expects an address, right? We don't just pass F1. If I have just F1 here, let me compile, we should get a warning. Actually, well, I'm getting an error based on the fact that these are pointers and I can't add them like that. All right, one of the warnings I get is I have an incompatible type for argument 1 of calc sum. So this error right here, all right, I need to make that an address. All right, so the address of F1 gets passed to this argument A, meaning A is going to point back to F1, B is going to point back to F2. I now need to make this adjustment here, right? Because these are pointers, we use the indirection operator to be able to read what's stored in their memory, right? And so now if we run the cursor, right, those are the only two changes we needed to make. But if we step into this now, right, A and B both have addresses. But if I say, well, okay, show me then the result of star A, right, show me the result of star B using the indirection operator, right, we can see that returns those two values. So sum, right, we add those two values, we assign that to sum's memory area, we're going to return that, right, back here in main, total gets that number. All right. Right. So all we had to do, right, is when we made these pointers, if we go back to the way this function originally was, let's just look at those changes one more time that we had to make, right? this was our original function, right? It just got copies of what's stored in A and B. Well, as soon as we made A a pointer here, then we had to pass the address of F1 to that pointer. Then as soon as A became a pointer here, in order to get to what's stored in the memory where A points, we had to use the indirection operator. As soon as we make B a pointer here, right, to read what's stored in the memory where B is pointing, we use the indirection operator. And then here we have to pass the address of F2 so B can point back there. Right. Now, what we want to take a look at is, now let me stop the debugger. What we want to look at is in here, all this function is supposed to do is add the values of A and B. Right. Well, what if this function, right, did something like always set B equal to 3? We don't want it to do that, but let's say you're writing code and you write something that has unintended consequences. Right. So let's just do a run to cursor here. Right. B now is pointing back to F2. Actually, let's run to here. Right. So we know back in main, F1 starts out at 1.01, F2 starts out at 2.02. B is pointing to F2 because we passed it F2's address. So now, when we assign a value of 3 to this, right, that means we have changed F2. When we come back to main, we're going to see that F2 now has a value of 3. We're not going to get the sum that we think we are because actually we're going to add 3 plus 1.01. Right, sum has 4.01. We're going to return that. And now, notice here, we're back in main. We changed the value of F2. Right? So since all this function is supposed to do is read the values that it points to, we want to make it so these pointers are read-only. And let me stop the debugger. In order to make these pointers read-only, all right, well, we know how to make read-only variables. We do that with a const operator. So now, if I put const here, what that means is I can read the addresses where A and B point, but I can't write to those addresses. So const makes these read-only, right? And now this should flag an error with a compiler, right? It does. So it comes up and says, error, assignment of read-only location, indirection operator B, right? This is a very safe thing to do, is if a function should not be making changes to the memory where it points, you make that pointer a const, right? That simply means it cannot write to that memory. And so now if we do a run to cursor, right, we're going to get the same result. Right, we're going to get the same sum here at 3.03. We're going to return that back to main, but there's no chance of accidentally changing the memory outside this area, the memory where we point to, right? We made those read-only. All right. So const makes the data to which the pointer points read-only, right? And that's a good thing to do if you're only supposed to read from that data. All right, now we'll go ahead and take a look at how to work with an array. So we're going to actually write a function that calculates then the sum of elements in an array. So what we'll do is let's stick with our floats here. All right, let's just make this, let's say size 10. And actually, fill the array with random numbers. Right. Now, if I use rand, we're going to end up with ints. So I'm going to say for int I equals 0, I less than 10, right, plus I. I can say F1, that's the name of my array, at index I. I want to store in it, I want to store rand random values. All right, I'm going to typecast them to a float. So I'll just call rand, right? And that will give me then any value, right, in between 0 and 32,767. And now I'm going to include the standard library, right, where rand is defined. And if I want to get numbers in a certain range, we could work with that. But let's just, for right now, just say we're going to fill the array with random numbers. All right. And we can do that here, but for practice with writing functions, so let's write a function that fills an array with random numbers. All right. So this function won't return anything. It's actually going to have access to that array's memory space. We'll just call this fill array. Now here in our example, we're working with floats. So it's going to be a floating point type. The empty bracket notation means that's an array. And let's tell it what the length of our array is. Right? It's going to need to know that. And then all it will need here is basically I'm going to cut this out of main. And now up here, remember the array is called A, not F1. It's called A. Probably don't need that comment since we have the other header comment there. It's going to fill our array with random numbers. When it's done, then, right, this is a pointer to the memory back here. F1 will be filled with random numbers if we call the function fill array. And we need to pass that the name of our array, F1, back here in main, and the length is 10. Right. And now if we write a function that sums the values in an array, all right. Well, that function then is going to sum up a bunch of floating point values, and it'll probably return a value of type float. So I'll call that sum array. It's going to need the array, which in this case is of type float. It's going to need to know the length. Right. And so let's create a variable sum. Let's initialize it right to 0. And then we'll say for int I equals 0, I less than length, right, plus I. Sum equals sum plus a at index I. And now we'll return the sum from here. And back here, let's have a variable called total. We can call it sum as well. And let's assign to total the result of, well, we'll call the function sum array. We'll pass it, then F1 is the name of our array. Here its length is 10, and I need to make one change. So when I copy pasted, right, this function shouldn't have 10, it should use length. Because the nice thing about this function is I can pass this function a floating point array of any length, and it will fill that array for me. All right, now let's take a look. These are things that we've done before, and we just wrote them in a way that we're familiar. All right, so run the cursor here. All right, so here in main, right, we have whatever garbage was stored in memory, right, in our floating point array. If we call then the fill function, right, and I'm just going to say next line because that we've seen how that works before. Next line. When we come back from that function now, here we see the functions filled in with these random numbers. Same way, if we step into this function now here, right, we're going to initialize sum. So we can see this function has two parameters. A points back to an address here in main where F1 is stored. And then length is the length of the array. Right? If we step through this, right, we initialize sum, we can see that we'll just go through and we'll keep summing up these values, right, until we step all the way through the array. Our for loop ends, we have our sum value, we're just going to return that, and we assign that back to the variable back here in main called total. All right, so that's how we know how to write functions now. right? Using this array notation, not using pointer notation, right? So let's start changing things one at a time. Let's start using pointer notation here in this fill array. So instead of the brackets then, we want to make this parameter a pointer. So we put the star in front of it that says A is a pointer to a floating point type, right? Since we know that this function needs to be passed an array, we still need the length. Right. Here, I won't have to change anything else in my function. We've seen in an earlier part of the lecture that we can use this subscripting notation here with A. Right. So if I compile, right, no errors, right? If I say go ahead and run the cursor, right, it fills my array, it returns my total back here. Everything works just the same, right? Incremental changes. So as you learn to work with these, right, we just made the one change here, where we made this a pointer. Basically, there's not a whole lot of difference between this notation. This says this is an array. Well, this says this is a pointer to some area in memory. It could be an array. It could be just, well, we don't know how much memory it points to. We're going to limit the amount of memory we access then by using the length of the array. Now, one thing we don't want to do here, since we need to change this memory, we do not want to put that const in front of it. If we put the const in front of it, that would make this array read-only, and actually we'd get a compilation error at this point, because this says, well, here we're trying to overwrite something we just said was read-only. So this is not a place where we want to use the const, right? Because we actually want to change what's stored in this memory. Let's go ahead and change then this array. So here, let's get rid of the bracket notation. Let's just put in the pointer notation. Right, and let's do a run to cursor. Right, we're getting the same random numbers every time. We're getting the same total back, and that's what we'd expect. All right. So notice here, the only change I made, once again, was to make this then a pointer. Now, since this should just be reading the information, this would be a good one to make a const, right? A should be read-only. All we're trying to do is read the values in the array. And so once again, if we do a run to cursor, it will rebuild. We'll still get the same results, but now here we safeguarded us accidentally overwriting memory. Right. Now let's make some other changes. We've got A here as a pointer. Instead of using this index notation, let's go to that pointer math notation that's at A plus I. Right. So we'll do that pointer math, which is really what the bracket notation was doing. If we do that and get rid of the brackets, then we have to write the star here, right? And that doesn't look quite as natural to us because we're used to that other notation. And same thing right here, we can do a run to cursor, and we still get the same results. We made the change now where we actually used the pointer math. We specifically said take A, which points to the start of an array, right, or start of some memory space, add I to it. Well, when we add I to it, I is an integer, but remember I is 0 through, in this case, 9. And that's the same thing as I times the size of a float. Right? It's doing that special pointer math, I times the size of a float. Right? So we're adding so many bytes as an offset from this base address. We could do the same thing here. Right? We can use the indirection operator and say, well, we want to now A plus I is A plus I times the size of a float. Go ahead and point to that area of memory and return that sum back to us. Right? And we still get the same results. We just have different ways of writing this. Right? Same results. The other way we can do this then without using any sort of index, right, is we are now going to create another pointer. So now I'm going to say float, and I'm going to make a pointer to A, and I'm going to set that equal to A. And now I want to make sure that pointer to A is less than, I'm going to keep A as the starting address. I'm not going to change that. A plus length. Well, A plus length is the address of A plus length times, where length is 10, when we call this with a value of 10. So length times the size of a float. That point's just beyond the end of my array. So we're just going to increment pointer A every time. And now here, we change this to dereference pointer A. Right. Same thing. If we do a run to cursor here, then this will still fill our array with these same random variables, right? I'm not seeing random number generator, so we get the same size. This will go ahead and calculate the total. Right. Similarly, if I want to write the same notation here, well then I'm getting rid of these, right? Pointer to A, I'm going to initialize that to A. I'm going to make sure that pointer A is less than A plus length. That's just beyond the end of the array. I'm going to increment pointer A, right? And then I need to use the indirection operator with pointer A here. If we build that, right, we run that back here, run to cursor, we get the same results. Right. These are all the different ways we've seen to do this with pointer notation. Right. Now, why do we do this? Well, pointer notation is often faster than the other operations. Just directly doing that pointer math is a little bit faster, right? Either one of these methods works. Any one of them works. If you have an array, though, that maybe has 1 million items in it, one method over another being faster adds up over time, especially if you're calling it the same function over and over. So whether you need it to be as fast as possible, right, often depends on the application. In this case, we want to do this to learn how to work with pointers, right, because they are part of our study of the C language. All right, so we talked about const, we talked about then constant parameters. All right, let's take a look at pointers as return types, right? We want to return a value from a function. All right, so we've got this function now that we filled with random numbers. Let's write then, so, find the location of the, actually, but first let's write a function that find the largest number in an array. Let's do that. All right, and we're just going to do it with notation with which we're comfortable. So let's stick with our floating point number. So we're just going to call this find largest. We're just going to pass it then, right, our array, which is of type float. Start out again with our index notation. We need to give it the length, right? And now we need to create some variable, right? And say, so let's create a variable of type float. We're just going to say that largest or maximum, right, is equal to, we're always safe to say it's equal to the first thing in the array, right? We look at the array list one at a time. First one we look at is the largest number. Right. Let's now iterate through the rest of the array. For int I equal 1, I less than length. And we now check, we say, well, if A at index I is greater than largest, then we have a new largest number, don't we? We'll just say largest, right, equals A at index I. And then when we're all done, we need to return the largest number. So return largest. And because largest is a floating point type, our return data type from our function is also a floating point type. All right, we made largest a floating point type because we're trying to find the largest of an array of floats. So now, if here, right, if we just made a variable down here, float max, right, and let's just say max is equal to what we call our function find largest. And then find largest expects two parameters. Well, here in main, my array is F1, the length is 10. Right. And now we do a run to cursor here. Right. And now if we step into this function, right up here, well, we're going to say the largest is the first element. All right, so largest gets a value of 41, and then we start at index 1 and we start iterating through the array. We say, okay, if A at index I, all right, if this is greater, then we find a new largest, which we did in this case, right? We keep going through that whole list of our array until we're done running the loop, right? Then this has the largest value, right? We return that. So back in main, max now has that largest value, right? So that's then how we find then the largest value. What if we want to find the location? So find the location of the largest number in an array. So we're still going to stick with this array notation, but now we're just going to say, well, the location will be an index, right? The location, in this case, if I use integer indices, so I'm going to say index location is equal to 0. Because here I'm setting the largest number to A at index 0. That means the location of my largest number then is stored in index location, and that needs to be 0. Here then, when we find a new largest number, we need to update the index location to I. Now when we return something, I want to return I, because I'm trying to return the location, which now is an index number. Since I is an int, right, my return data type changes. And here now, then I need something called maybe max location. Right, since that's an integer index, I'll do that. And then here we'll stop the debugger. And so now when we run this, right, run to cursor, we come back. Oh, let's see, build failed. All right. Return I. Oh, that's a problem. I can't return I because I declared I to only exist in here. I didn't want to return I. It goes out of existence, right? I want to return index location. All right, so back here in main, it says index location 7. Let's open up our array. Let's look. Okay, the largest number is, it looks like the largest number is 29,358, which is stored at index 7. All right, so that worked then for returning that integer index location. All right, but now let's see then, we said what we want to do is we want to return the pointer. Right, so we're going to find the location of the largest number in an array. So what we want to do is we're going to say, find the memory location. Right. And we want to return the memory, or return the address of the largest number. Before we were returning an index, and if we wanted to find that, we could have then back here in main said, well, F1 at index max location, then that's the largest number to find the largest number. But now we're saying we want to return this as an address, right? Because we're going to return it as an address, right? We're going to see that our return data type here is a float star, a pointer to a float. And now instead of index location, what we want to do, well, actually, here's what we can do. I can still leave this as an integer. I can still iterate through the array like this. But now when we return this, what we want to do is we want to return the address of A at this index location. Right. So if I return A at this index location is where the largest number resides. If I return its address, well, this is then the address of a float, which is a pointer to a float. My return data type is a float star. Back here, then, I need to say, well, I need to have the same data type. Max location now needs to be a float star. Right. And let's see, run the cursor. All right, so back here in main, max location now has this address. Let's go ahead and type in the address of F1 at index 7. F1 index 7, where we know our largest number resides. They're the same address. Right. So in order to return, right, to have a pointer as a return type, it has a return data type. In this case, it was float, and then it has the star. That indicates that this function is going to return a pointer to a float. Right? We did so by not having to make very many changes here, but here instead of returning the index location, I had to return the address of A at that index location, right, by using this notation. Otherwise, I could change this out if I now change this to a pointer to A. I can still use the same notation, right? I don't have to change anything else. This will still work. Actually, yeah, that will still work. All right, I still get the same results. All right, didn't have to do much there. All right. Now, if I don't want to use that pointer notation, I just want to say now I'm going to make largest a pointer. Now I'm just going to call this PTR, pointer to largest. And now I am going to store A in that. I'm going to get rid of this whole index location, right? I don't need that variable anymore. And now I'm going to create a float pointer to A. I'm going to set that equal to A plus 1. Right, just one location, that's the same as A at index 1. And then as long as pointer to A is less than A plus length here, and now I'm going to increment pointer to A every time. And now I don't use A at index 1, I use the indirection operator with pointer to A. And I say, if the number stored there is greater than, well, now I have pointer to largest, so I need to use the indirection operator with that, right, to read that memory, because that's pointing to the memory location that has the largest number. So I'm going to compare the number here with the indirection operator with the number here. And if this is now the largest number, I just say pointer to largest. Well, point that to the current location of pointer A, and then when this is all done, right, I return pointer to largest. And I have less code than what I did in that previous example. Before, we had to keep track of the largest number and the index location. Now, all I need is to keep track of this one variable, pointer to largest. Right? So we have less variables. We're taking up less memory. There's less things to push onto the stack and pop off of the stack. Our code will move a little bit faster than it did before. But let's see. Now when I call this function, I don't need to change it because F1 is a pointer to an array. Here, I likely want to make this a const. So if I make this a const, right, and it says that's read only, well, I'm only trying to read from that. And I need to make this a constant too, because I'm now creating another pointer that points to it. So I had to make that a constant so that will maintain its read-only status. And I'm killing the const qualifier here because this isn't const. But if I do this, I can't read. Yeah, this is getting ugly. All right. Let's take the const qualifiers out of there and get rid of, okay. Oh, here. I had an error here. I wasn't paying enough attention from a change I made before. All right. Incompatible types when initializing float. Oh, sorry, when I got rid of it. I need the star there, right? I forgot to make that a pointer. All right, variable max location set but not used. Well, I'm going to use it here because I'm using it elsewhere. I get the warning. Same way with total, right? When it says I'm not doing anything with that. But let's go ahead and do a run to cursor. Ignore those warnings. Now we should get back the same address here, right? After this runs. So here I'll just say, go ahead, step into this, right? We're going to watch this iterate through. This address is going to change where this is pointing. Right. Eventually then this will settle to, right, it's going to return the address back here, right? Store that in max location, the same address as F1 index 7, right? So the pointer notation takes some time to getting used to, right? Traditionally, this is one of the most difficult things for students learning to program, right? Getting used to pointers, addresses, the way these things work. We have to think a little bit more about what we're doing with memory, right? But you've seen an example now, right, of how to take functions that you knew how to write and turn them into functions that require pointer notation. And in this case, you also saw an example where we're returning a pointer back from a function. Right. All right. That's enough on this topic for a while. We'll go over a few more examples in class.